This is part 8 of the series Right Triangles and Trigonometry, and up to this point we've had the luxury of working with triangles that gave us a specific kind of information. We've either had enough side lengths to determine the other side lengths using Pythagorean theorem. We've had special right triangles where we've been given a special configuration of angles which allowed us to find the side lengths of the triangles. More often than not, we're not going to have those luxuries. We're not going to be able to apply the theorems that we've looked at so far to solving for right triangles, that is, to find missing angles and missing sides. So we're going to need another set of tools, and those tools come in the form of what are known as trigonometric functions. And the trigonometric functions come in three basic flavors. They're sine, cosine, and tangent. We abbreviate these SIN, that's pronounced sine, not sin, COS, which is still cosine, and TAN, which is pronounced tangent. Now, from time to time, we'll abbreviate cosine and tangent with cos and tan, but more often than not, it's sine, cosine, tangent. Now, to be able to work with these functions, it's important to understand what they do. And before we can understand what they do, we have to have some common language to work through these triangles. Let's take this angle. That letter there is the Greek letter theta. Characteristically, in trigonometric functions, Greek letters are usually used to denote angles, but we're going to use all sorts of letters to denote them, from our standard alphabet to Greek letters to other symbols. But this is just a demarcation of an angle. Now, the idea of adjacency and oppositeness is a critical factor here. If we started this angle and we want the angle opposite, the side opposite this angle, we would go from the vertex straight across to the first side we encounter. So in a straight line from the vertex across, that is opposite. So this side is the opposite side, and that's what the O stands for. If we just want to go next door to our next door neighbor, that would be adjacent. So right next door is adjacent. And this side is in fact adjacent, but we don't consider it so because it's always the hypotenuse, because it's the side opposite the right angle. So here we have opposite and adjacent. Now, if we were talking about this angle, then we drive from this vertex straight across. This side would be opposite to this angle. This side would be adjacent to this angle, and notice this is still the hypotenuse. So it's really important that you understand the distinction between opposites and adjacent. Opposite and adjacent. Now, when we talk about the trigonometric functions, think of these things as little machines, and each machine takes an input and generates an output, something like a blender. If you have a blender, you put in some fruit and whatever else you want to mash up, you turn it on, and out comes something else in a different form than what it came in. That's what sine, cosine, and tangent do. Now, more specifically, sine, cosine, and tangent generate relationships between the angles and the sides of a right triangle. So let's take a look at these values. Here, the sine function takes in as input the angle, and it spits out the ratio of the opposite side divided by the hypotenuse. So sine generates a ratio, generates a number, which is the ratio of the opposite to the hypotenuse. Cosine generates a ratio of the adjacent to the hypotenuse, so adjacent to the hypotenuse. And tangent generates the ratio of the opposite to the adjacent, opposite to the adjacent. Now, with the combination of these three, given any other two values, given an angle and any one of the three sides, you would have enough information to find the remaining angles and sides of a right triangle. And we're going to go through many examples to show you how that's done. Let's go ahead and put these ideas into slightly more concrete terms with an example of a triangle with numbers associated with it. If I were to say that I wanted the sine of angle B, so I want to talk about the sine of angle B. So we're talking about this angle, and before I can do anything practical, I need to understand what's being asked for. So sine of angle B. This is how we write it. The sine, angle B is the input to the sine function, equals. Now, as I said, sine, cosine, and tangent generate ratios. So the sine of angle B is going to generate a ratio, and it's the ratio of the opposite to the hypotenuse. So it's the opposite to the hypotenuse, 5/7. So the sine of angle B is equal to 5/7. Now you'll notice we don't even know what this angle is. And that's okay. It doesn't really matter because, again, the sine function simply generates the ratio of two particular sides in the triangle. Now you may think to yourself, holy cow, how am I going to ever remember these three things? Well, there's a silly little limerick that I learned when I was very young that should help you work through this. And it's fairly straightforward. And as I read through this, follow along, and I'll explain how we do it. Some, sine, old horse, caught a horse, taking oats away. So again, that's some, old horse, caught a horse, taking oats away. Now how it's used is you always start at your target angle. In this case, our target angle is angle B. So we start at angle B. And we run through the limerick. Some, old. Old is opposite. So O stands for opposite. Opposite from angle B is 5. Horse, hypotenuse, horse. Some, old horse. Some, old horse. And that's all there is to it. Now, you're going to see that you're not always going to have enough information for the first one to work every time. So each time you need to go through it, you simply go back to the original angle and try again. Now, if I wanted cosine of angle B, so let's say we want cosine of angle B. Some, old horse, that was sine. Caught, cosine. Is adjacent. 3. Horse, 7. So again, caught a horse. So caught a horse. And tangent of angle B is taking oats, opposite. Oats away, adjacent. Taking oats away. Taking oats away. And in case you were wondering, we're always only going to be doing the acute angles in a right triangle. We will never use the right angle in sine, cosine, or tangent. It's pointless because those angles don't generate the values that we would expect. These are very simple values, and we're not going to get into that right now, but sine of 90, cosine of 90, and tangent of 90 have very specific values that are only useful in analytical terms, and we're not going to be using them. All right, let's switch to angle C now. I want to do the same thing, but this time with angle C. So I want the sine of angle C. again, we start at the angle, start at the vertex. Sum, old, this is opposite, so old, horse. Sum, old, horse. Sum, old, horse. Opposite over hypotenuse. Cosine of angle C. We go back to the angle, cot, adjacent, horse, hypotenuse. Cot, horse. And tangent. Taking, back to the angle, oats, opposite, away, adjacent. Taking, oats, away. And that's all there is to it to set up a sine, cosine, and tangent ratio. Now we're going to be working with combinations of these to actually find various sides of triangles. But this is the general idea. Remember, sine, cosine, and tangent simply output ratios. And they're the ratios of two different sides of your right triangle. We're always going to work with acute angles and never with the right angle. The right angle serves only to pinpoint what our hypotenuse is, because the hypotenuse is opposite the right angle. All right, let's look at a more practical example. In this example, you'll notice we only have one angle, we have one side, and we're looking for side Y. So what we're going to do to find this side, we're going to start with the only angle we know. If we wanted to, we could figure out what this angle was and use this one, but why do extra work when we don't have to? So we're going to start here, and we run through our limerick. Sum, old, horse. Wow, we got lucky. So it's the first one out of the box. Sum, old, horse. So let's write that down. Sine of 34, the angle goes into the function, equals sum, old, horse. 7 over y. Now we have to solve for y. This is just a basic algebra problem. Multiply both sides by y, multiply by y. This gives us y, sine 34 equals 7. And then we're going to divide by sine 34. This is simply a number. Don't let this fool you. Remember, sine, cosine, and tangent simply generate ratios. So y equals 7 over sine 34. And to solve this, we simply bring up our trusty calculator and enter it in. 7 divided by sine 34. And that's our value, 12.5 approximately. Now you'll need to remember that these functions, sine, cosine, and tangent, always generate approximations. These are approximate values unless we're dealing with specific angles like 30 degrees, 60 degrees, 45 degrees, things of that nature. For the most part, you're going to get odd angles and you're going to get approximate values. So your answers are almost always going to be approximately equals some number. So again, just to recap, it was sum, old horse, sum, old horse. We solved for y by multiplying by y to bring it into the numerator, and then we divided by sine 34 because it's just a number, a ratio. Divide both sides by sine 34, y equals 7 over sine 34, and we put it in our calculator. In the next session, we'll continue on with more of these examples and go into some more advanced examples. I hope this was helpful, and I'll talk to you in the next session.